Thank you very much, Ettore. And a warm thank you to you and the other organizers for the very kind invitation at this conference. I'm more of an elliptic guy, so for me it's a particular pleasure to be here, being exposed to this community, working on problems that I'm, in principle not really familiar with, but maybe there are connections. So concerning my talk, well, the title is a bit bold. So what I mean here is, so there's a rich story of basic, say, calculus on metric measure spaces. So metric in the sense, in the elliptic sense, not Lorentzian sense, so really distances. And I want to go through some of the things that have been done in the past in this context. So there is no Lorentzian length space, basically, in my talk. And why I do that? Well, because this sort of calculus that I'm going to overview, or at least glimpse on in my talk, has been extremely successful in the study of RCD spaces. In fact, to the extent that even the very definition of RCD space is partly based on these sort of tools. Okay, so CD spaces alla Lost-Turm-Villani concern convexity of entropy functionals along Weierstein geodesics. RCD is that plus something concerning Sobolev functions. In particular, we should know what Sobolev functions are if we want to study RCD spaces. Now, of course, we should be aware that even though these sort of tools that I'm going to overview today have been successful in the elliptic setting, this has a priori no implication on whether they will be either well-defined or useful in the Lorentzian setting, right? Per se. But I guess it's worth a shot. I mean, let's have a look to see whether the previous experience in some sense can give something in this direction. And in fact, a proper subset of what I'm going to discuss, in some sense, the sort of program is already initiated. In fact, it's been initiated in Toronto, the conference, the semester, thematic semester that Minguzzi already mentioned in the opening address. So this program has already started, and I guess with the relevant subset of the audience present over here, and Argam is going to give a talk about this in the last talk of the conference, and I think that we can say something interesting both in the non-smooth Lorentzian setting, but I think that some of our findings, I mean, I dare to say that perhaps they're interesting even in the classical smooth Lorentzian setting for what concerns Lorentzian geometry. But for that, I mean, I'm building up a little bit of hype for this talk in the last conference. So, yeah. All right. So, very briefly said, you can put layers on calculus according to how many derivatives you take. Zeroth order calculus is where you don't take any derivative; you just pick your ruler and measure stuff. First order, you pick, you consider first order objects like speed of cars or differentials. And the second order, then we have things like Hessian, covariant differentiation, and curvature tensor. So it's pretty clear that whenever the zeroth order calculus is sort of by definition available on any metric measure space, because you have a metric and you have a measure. It is also quite clear that you cannot hope to go beyond second order calculus if your assumption on the metric measure space is a curvature bound, right? For the same reason, you cannot do more than, I don't know, C3 analysis over a C3 manifold, okay? If your assumption is of a second order nature, like a curvature bound, then you cannot hope to go beyond second order curvature. Now, one thing that is a priori non-trivial is that on any metric measure space, there is a well-developed or well-developable first order calculus, okay? So a first hint in that direction is that on a metric space, you have a distance, so you can define, say, Lipschitz functions. And Lipschitz functions is, in some sense, a sort of functions with bounded derivatives, if you wish. So that hints toward the possibility of developing first order calculus. Please. No, that is inside. That is inside. Yeah, I allow discrete. So yeah, perhaps fair enough. So if I don't put curvature bound, my metric measure space is just a set with a distance, positive satisfying the, not reverse triangular inequality, the standard triangular inequality, and a measure which is radon and finite on bounded sets. Okay, and then on curvature bounds, well, we will have assumptions. All right, so let's go through this. about first order calculus. I guess a starting observation. So I guess as a general rule of thumb, whenever it is possible, whenever you have a variational interpretation of some differential object, typically that is helpful for getting hands on that object in low regularity, right? In some sense, if something minimizes or maximizes some functional, you have one more derivative thanks to Euler equation, if you wish. And that is extremely useful if you work in low regularity setting. So let me start with the following trivial observation. Say that you are on RD or a Riemannian Fisher manifold, but a smooth setting. Well, then if you have a smooth function f, the modulus of the differential is the least continuous function such that this inequality holds for any smooth curve G. Okay? It is rather clear that this is, is true for any, because f composition, f evaluated gamma t is smooth in T, then you differentiate and you are there. And it's also clear that if you take a function which is too small, so smaller than modulus of the f somewhere, then by continuity should be smaller than a neighborhood, and then basically you can easily violate that inequality. Right? Okay, so this gives a variational approach for defining modulus of the f. And I want to, to use this kind of idea to define a Sobolev function, and this requires on metric measure space. And this requires basically to do two things. So first of all, I should understand what it is speed of a curve for a curve in a metric space, but I don't have gamma prime, but maybe I get modulus of gamma prime. And also I should do something to handle the fact that even on RD, for a Sobolev function, this inequality does not hold for any curve. I should do some sort of integration or something like this, because Sobolev functions are typically only defined almost everywhere. All right, now, for what concerns the metric speed, there is a well-established notion. I'm not so sure who came out first with this notion. For sure, it was known to De Giorgi in the 80s, but maybe the Russian school was also familiar with this concept. So let's say that a curve gamma is absolutely continuous. Well, if the absolute continuity inequality is in place, so if there is some L1 function f such that the distance between gamma t and gamma s is bounded by the integral from t to s of this function f. For instance, Lipschitz curves are absolutely continuous, and in that case, you can take f, the Lipschitz constant. Now, it is again. Let me use a variational approach. So there will be for sure a least function f for which this is true. Okay, if I have two functions f1 and f2, and I take the mean of the two, it's easy to check that also the mean satisfies that. Okay. So and also the limit of a decreasing sequence by basically monotone convergence also satisfies this inequality. So there is a minimum such f, and I call that metric speed. Okay, it is a little bit less obvious, but not too hard to check, that this metric speed also satisfies this limiting relation for almost everything. Okay, so in particular, this ratio has a limit for almost everything as soon as gamma is absolutely continuous. Okay, all right. Then what about Sobolev functions? So well, first of all, if you've never seen this, for me it was surprising to realize that one can define Sobolev functions, real-valued Sobolev functions, over an arbitrary metric measure space, so where a priori integration by parts is not there. Now there's a long story behind that. The story began with works of Ayuwash, who was the first to attempt such a definition, but in some sense his definition is, well, let me say, in some sense, not the correct one, or at least not the one that I'm going to use here. The one that I'm going to use here is equivalent to those defined first by Chiger and then by Shammugalligam in 20 years ago, well, a bit more. Although I will take an approach that has been introduced by myself together with Ambrose and Savare about 10 years ago. So you recall that I mentioned that I want to use this variational approach to modulus of the differential to define what the modulus of the differential is in some sense in a metric measure space. But I want to integrate along curves in some sense. And to integrate along curves, I use the concept of test plan. So a test plan is a probability measure over the space of continuous paths, okay? That satisfies two properties. So the second is perhaps the easiest to understand. So the total kinetic energy is finite. Right? So we have defined the concept of metric speed. I just squared it, integrate, and want that integral to be finite. And the first condition is about this. I have evaluation maps ET that take continuous curves over the space X and return points on X. And the evaluation just takes a curve gamma and returns, gamma at time t. That's what it does. So if you have a measure on the space of continuous paths, and you do ET push forward such measure, you get a measure on the base. Do you have a question, Robert? Yes, all zero. It's all zero. All zero. All zero. I mean, the definition makes sense, right? It's trivial. It's trivial. If the space, so on discrete spaces, every function is Sobolev with zero differential. So the definition is there. It's just, much like, if you want, much like on any discrete space, any function is locally Lipschitz, and locally the Lipschitz constant is zero. So, I mean, okay. But that, so in that sense, there is coherence on the theory. Then I agree with you that the calculus is, I mean, you give definitions to produce theorems, and this sort of approach is basically tells you nothing about a calculus on discrete spaces. In fact, so there are other settings where, so there is an intermediate setting where the space is maybe is not discrete, but has no Lipschitz cars or absolutely continuous cars, like fractal, von Koch-Carver, and so on. Even in that setting, for the same reason, basically every function is solved with zero differential. Now, although on fractal you might want to do, Laplace and Dirichlet forms and so on. So in that case, you have to modify the definitions, and people do that. There are different approaches. Okay. Right. Yeah. So what I was saying, yeah. So we have these evaluation maps taking curves on the space and returning points. Now, if I have a measure on this space and I do ET push forward such a measure, I get a measure over here. And the first requirement over there is that this measure should be diffused, in a sense. Okay? Should be less or equal than some constant times the reference measure M that it is given in my metric measure space. And for some C that depends on pi, but not on T. Okay? Makes sense? So in some, typically, a direct mass over a single curve, regardless of how nice that curve is, will not be a test plan because the marginal will be, a delta, right? So that in some sense. So notice that the concept of test plan uses both the distance in order to compute the metric speed and therefore the kinetic energy, and the measure in order to compute this so-called bounded compression property. Now, if we have this, we can define now the concept of Sobolev function as follows. Well, I say that I have a function in L2. Well, then I say that it's in W2, provided there is some non-negative L2 function G, for which this inequality over there is true for every test plan, right? So it's basically the same inequality that was written a couple of slides ago, but just integrated with respect to test plans. Okay? Of course, this by no means is defining the differential of f, right? Perhaps I should have clarified this. If I want to know when a function is Sobolev, that's perhaps the starting point. If I want to know whether a function is Sobolev, I don't need to know what the differential is. I might be satisfied to knowing what the modulus of the differential is, and that if that guy is in L2, then I call my function Sobolev. So, okay, and now here it requires a little bit of work, but not too much, to check that there exists a minimal G in the almost everywhere sense, and I will denote it modulus of the F. Okay, for historical reasons, this is called minimal weak upper gradient, although it is in fact a minimal weak differential. But the name is there, and I won't try to change it. But I will denote it this way. Of course, at this level, I'm slightly cheating, meaning there is no df whose modulus I'm picking in order to compute this guy. There is just please. This. Gamma 1 and so pi is a measure. So thanks for the question. So pi is a measure on the space of curves. So gamma is a curve, and evaluating gamma at time 0 is a point on which I'm evaluating f, and gamma at time 1 is another point. Yes, sorry, okay, yes, sorry, yes, thank you, yes, yes, sorry, this might be confused. You're right, sorry. Yeah, even here, right? I'm using this notation where the subscript does not mean derivation, but evaluation. Sorry, thank you for this question. Yes, this might be confusing. Yes, thank you. Right. Other questions? All right. Perhaps I should notice that, there is nothing special about the case p equal 2 in here. If you want to define W1p functions, well, then simply you do the same, except that in defining a test plan, you raise this to the power q. So you want sort of a pq duality in here. So we hold that conjugate exponents. But for simplicity, I will stick to the case p equal 2, just for simplicity. But everything I'm saying holds more generally. All right. Yeah, a couple of interesting properties or basic properties of this space W12 that I just defined. So first of all, if we pick this definition and apply it on RD, a Riemannian manifold, or a Fiesler manifold, it reproduces the classically defined notion through integration by parts. And in this case, modulus of the F equals the norm of the distributional differential almost everywhere. Okay? It's not entirely trivial, but it's not even that hard to check. I mean, if you work a little bit with a bit of proficiency in this sort of calculus, you get this. So in some sense, this justifies, so because of this, you know, I'm right, or perhaps Chigger was right in calling this guy W12, right? By consistency. Now, another property is that W12 is always a Banach space whenever I equip it with its natural norm. So who is this norm of a Sobolev function? Well, just the square root of the sum of the squares of the norm of F and of the distributional differential. Why Banach and not Hilbert? Well, because of this, right? I mean, it is clear if you think about this in a Fiesler setting, say RD with a norm, then the norm of the differential that you're using is the dual of the norm in the base space, right? And that typically does not satisfy the parallelogram rule. In fact, it does if and only if the base space is Hilbertian. So you should not expect W12 to Hilbert just because the norm of the differential in general is not an Hilbert object, even in a smooth category, right? If you consider also Fiesler structures. And in fact, in this sense, perhaps let me emphasize that this is, is an interesting observation even for what concerns what will come next, because this concept of Sobolev function, in some sense, allows us, you see here from this line, allows us to detect, in some sense, norms on tangent, or perhaps I should say cotangent spaces at almost every point, right? So we don't have a tangent space on metric measure space, in principle, maybe, I don't know. But this guy, in some sense, is seeing what happens in that cotangent space and allows us to check or to verify whether on that cotangent space I do have an Hilbert or not Hilbert norm, according to whether this guy is Banach or not. And finally, say that you don't like the concept of metric speed, say that you don't care about general metric measure spaces where things can go crazy, as Roberto was mentioning, say that you only care about spaces with curvature bound. So this CDK infinity condition is the Loss-Turmbillani condition that the entropy is convex or K-convex along Bart-Stein geodesics. Well, in this case, you really don't have to care about all test plans. It is a theorem that you can check this inequality just for pi's that are concentrated on constant speed geodesics. In that case, the definition simplifies a little bit because you don't have the metric speed over there because that is constant and is constantly equal to the the distance between endpoints. So in some sense, this is a little bit like you can recognize a Sobolev function over RD by just differentiating along coordinate axis, right? Or straight lines in particular. And this is a kind of an analog, under a curvature condition. You have many geodesics, and you can just differentiate along them. Yes, absolutely. That is crucial. Yeah. Everything as before, plus concentrated on geodesics. All right. Okay. Now I want to go, to go on with calculus, and I want to try to convince you that not only we do have Sobolev functions and modulus of distributional differential, but we do actually have a differential. It's possible to define as a linear operator. And in order to define that, I need to give a couple of definitions. So the first one is the concept of L2 norm del infinity module. So an L2 norm del infinity module is basically a Banach space equipped with two additional structures. So the first of all, is a module over the commutative ring with unity of L infinity functions. So it is a module in the algebraic sense. And moreover, there is also some analysis over here, and the analysis is that there exists a pointwise norm. So there's a map which takes elements of my Banach space and returns L2 functions. And this map should be almost surely non-negative. It should respect the product by L infinity function. So pointwise norm of F times V equals the absolute value of F times the pointwise norm of V for any vector V in my Banach space and every L infinity function. And finally, I can use this pointwise norm to recover the initial Banach norm in my Banach space just by taking the L2 norm. Now, what is this? So take the space of L2 vector fields over your preferred Riemannian manifold. Well, this is an L2 norm del infinity module in a trivial way, right? It's a Banach space, in fact, it's Hilbert, and you can certainly multiply a vector field by an infinity functions, and it remains an L2 vector field, and you can evaluate the norm of vector field almost surely. More generally, in fact, whenever you pick the space of, say, L2 sections of any normed vector bundle, that by nature is an L2 norm del infinity module, at least as soon as this normed vector bundle is made by complete spaces. So the idea, which is extremely classical if you are in algebraic geometry or differential geometry, is to observe, and in this setting it goes back to work of Weaver and perhaps even earlier by Savageau. So is that in life, basically, you can describe vector bundles or homogeneity bundles either by describing these sections at every point and then describing how these sections are glued together, or you define a bundle by just describing its fibers, okay? So that you encode the regularity of the bundle in the regularity of the fibers that you're going to consider. Now, what we can do here is give up the idea of defining a tangent or cotangent space at every point or almost every point, and just think as L2 norm del infinity modules as this space of L2 sections of some bundle, which is not really given, but okay, but still, maybe as far as these objects will allow us to make computations and deduce theorems about the structure of metric measure spaces, I guess we can be happy anyway. I should mention that there are recent works of Di Marino, Lucic, Pasqualetto, and a bit also of myself that in some sense corroborate this interpretation, in the sense that every L2 norm del infinity module is in fact the space of L2 sections of some given bundle, but I won't insist on this point, and I will be satisfied by this more abstract viewpoint, if you wish. Now, what has this to do with Sobolev calculus? Well, the theorem is the following, basically. You take any metric measure space, and well, then there exists a unique couple up to unique isomorphism, L2 T star xd, where L2 is an L2 normed module in the sense that I just described, and D is a linear map taking Sobolev functions and returning elements of this module, and such that two things are true. So the first, whenever you pick a Sobolev function f, you compute D of f, and then you take the point-wise norm, what you end up with is exactly the minimal weak coupling unit of f. And the second property is that if you take all these D of f's and you take L infinity linear combinations of them, what you obtain is dense in this guy. Okay. So of course, so up to unique isomorphism means that the structure is extremely rigid. So if you have another couple, so in this sort of theorems, you certainly have a certain degree of flexibility. I could always take another set with the same cardinality as L2 T star x, pick a bijection between L2 T star x and this set, and then define a new D, by post-composing with this bijection. So in some sense, I can inherit the structure. But that's basically all the freedom that I have. So basically, all the freedom that I have is how I call the elements of this L2 T star x, because otherwise the structure is extremely rigid, because you have up to unique isomorphism. Okay. Now this is both a good and a bad news. It's good because if you buy this definition of L2 normed modules, well then this D you should think of as the differential of a function, and this L2 T star x should be the space of L2 one-fourths. Okay, in some sense there is no other possibility. It could be a priori, it could be a little bit dangerous because this differential is only defined through these two properties, and there are other properties of the differential that you might want, and that a priori, that might be not there, but at least a couple of these are. So first of all, this abstract differential is a closed operator as a map from L2x to L2. This is the classical L2 space, and this is the this cotangent module in the sense that I just described. So it is a closed operator in the sense of unbounded operator between Banach spaces, and it satisfies the Leibniz rule in a very natural way. So it's not evident, it's not apparent from this definition, but it does. So the differential of f times g is f times differential of g plus g times differential of f for any couple of bounded Sobolev functions f. Right. Okay. So now let's go back to to our understanding of the tangential structure of metric measure space, and one can say that a space is infinitesimal Hilbertian if W12 is Hilbert. So as I was saying before, this in some sense is like telling that on tangent spaces, or on almost every tangent space, the norm, whatever it is Hilbert, right? So this should, instead of detect metric measure space that are more Riemannian-like than Finsler-like. And then once you have this definition, you can define the RCD condition by adding infinitesimal Hilbertianity to the Loss-Turm-Villani condition about curvature dimension. Now, a couple of comments are in order here. So first of all, as I mentioned, in the smooth category, a Finsler manifold is infinitesimal Hilbertian if and only if it is Riemannian. So at least in the smooth category, this recipe works. Now, the second point is infinitesimal Hilbertianity, unlike the curvature dimension condition, is not stable by measure of Gromov convergence. These weak notions of convergence that we have also discussed in this conference. Is not, okay? In fact, the class of infinitesimal Hilbertian spaces is dense in the class of all metric measure spaces. How do I know? Well, because every metric measure, for trivial reasons, every metric measure space is approximable by discrete spaces. On discrete spaces, every function is Sobolev with zero differential. So in that case, the space, this cotangent module L2 is just the zero space. So it's Hilbert just because it contains just one point for trivial reasons. Okay. Now, what is interesting is that the RCD condition that is stable. Okay. And a way to read it, the way I think about it, besides technicalities, is that so infinitesimal Hilbertianity is a first order condition. So per se is not stable under a zeroth order convergence. But if you couple it with a second order bound, like a curvature bound, then first order properties pass to the limit, right? Much like in the same spirit that derivative of functions do not pass to the limit if functions converge, say, up to zeroth order. But for instance, for a sequence of convex functions, the differentials or subdifferential do pass to the limit under, say, uniform convergence. Okay? In practice, the stability of this notion, proving the stability of this notion required a little bit of work. And so the basic point is that there is a well-defined heat flow on Loss-Turm-Villani spaces, and that heat flow is stable. That was a result in my first paper on the topic, and this was the beginning of a story about studying the heat flow on metric measure spaces. That actually, a few of the collaborators here are present, Shinichi and Andrea. And I should also mention that the first time an RCD kind of condition appeared, it was in a paper together with Ambrose and Savare, where we were investigating this precisely from the point of view of the heat flow, and specifically for the case n equal infinity. All right. Perhaps, let me mention a couple of things. So what can we do with this calculus? Well, for instance, once we have this concept of differentials and pointwise norm of them, we can integrate by parts and define a Laplacian. So here is a possibility. For instance, and for simplicity, I'm sticking to the case of infinitesimal Hilbertian spaces, but in fact, what I'm going to say holds more generally, even with potentially nonlinear Laplacians. So certainly, if I'm on a space which is infinitesimal Hilbertian, by polarization, I can define the FDG. Right? And this is clearly, it's easily seen to be bilinear. And then I can define, a notion of Laplacian bound. Say that I have a function which is Sobolev or locally Sobolev. I haven't said what locally is, but say the space is compact. So for instance, local doesn't matter. And if you have a random measure, you can give a meaning to Laplacian of f is less or equal than a certain measure, provided that so you can interpret this now in the sense of distribution, because now you can integrate by parts. Right? So you can say for any Lipschitz function g, say we bounded support g non-negative, this inequality holds. Right? If we were in the smooth setting, this would really be the distribution of Laplacian. That's really good. All right. Now, why this matters? This matters because, so this is in some sense a first non-trivial theorem concerning calculus, the link between, well, not, first in this talk, but not historically the first, between a link between this Sobolev calculus and this curvature dimension condition, because if you pick an RCD zero-n space, so what is an RCD zero-n space? It is infinitesimal Hilbertian, and just, let me remind you that the CD zero-n condition reads in one of its equivalent formulations as the convexity of the Renyi entropy. So basically, you pick a function much like the Boltzmann entropy, but rather than integrating z log z, you integrate this function, so minus z to the power 1 minus 1 over n. Okay? And you ask this to be convex along W2 geodesic. Well, then, if you have such a space, then the Laplacian of 1/2 distance squared from a point is bounded from above by n. So this is a non-smooth analog of the classical statement by Calabi about Laplacian comparison in smooth Riemannian manifold, even in points where the distance is a priori not smooth. Okay, Calabi was interpreting this in the sense of barriers, and here I don't have barriers, at least in this generality. Although recent works by Mondino and Simon, in some sense, pushed calculus up to that sort of viscosity sense, sense close to that of barriers, but at least this statement has a meaning. Okay, so that's I guess the first point. And the second point is that not only this is a meaning, but it's actually true. Meaning, this is a theorem, so you can prove it. Now, perhaps I will. Let me actually give I have 10 minutes, right? So yeah, perhaps I should have time to give an outline of the proof. And how we can prove this? So the idea is this. So pick a probability density and consider the geodesic connecting it to the direct mass at the point x. So the point x is the one where we want to study the Laplacian of distance squared from x. So x is that point over there. And I have such a geodesic along which this functional un is convex. For simplicity, I'm assuming that these densities are, these measures are all absolutely continuous, although a priori, this requires a little bit of work. But let me skip some detail, let me cut some corners, let me focus on the main point. So the main point is that, so I'm combining now the W2 convexity of the entropy that comes from the CD 0 n condition, together with the convexity of the function, minus z to the power 1 minus 1 over n. So the first inequality over here is trivial because, so this is really inequality. Let me write it in a simpler form. Whenever you have a convex function, it is a triviality. So f is a convex function of 0, 1. It is a triviality that f of t minus f of 0 divided by t, this is less or equal than f of 1 minus f of 0, right? So that's by convexity. So in this case, f of 1 is the entropy of the direct mass, which is 0. So it's not appearing in this inequality, and there I take the limit just because I will. Now this limit is the same. I'm writing just the definition of what is this entropy functional, and then here I'm using the fact that un is a convex function. So if I evaluate this convex function at one point and minus in the other point, I get this sub-differential kind of inequality, right? So that's I've done nothing except using the the convexity of the entropy over here. Now, it's a matter of running computations basically to show that in order to conclude the proof of the Laplacian comparison, I just need to prove this first order differentiation formula. Because if I prove that for any, say, Sobolev function g, I do have this derivation property. So this is telling me how much is the derivative of g along a Spacetime geodesic. So I'm really differentiating a function along a curve, in some sense, as much as I would like to do in a smooth setting. Because if I do this and I plug the result in the inequality above with g equal un prime of rho, I get this inequality, which is basically the Laplacian comparison estimate, right? So this function un of rho is my arbitrary test function, and if you write down what that means, is perhaps there is I might have be missing a minus sign, but the point stands. Okay, so we need just to prove this differentiation inequality. And how can we differentiate a function along a Spacetime geodesic? Well, the basic observation is this: is that for any Sobolev function f, if mu t is our geodesic that I was, Spacetime geodesic that I introduced in the previous slide, and I differentiate at time t equals 0 the integral of f in d mu t, well, then I can bound from above this by this quantity over the right-hand side. Now, where does this come from? Well, it's basically almost the definition of Sobolev function. So from the definition of Sobolev function, you know that you can bound the integral of f in d mu t minus the integral of f in d mu 0 with something which has the differential of f and the speed of the curve, and actually the distance between gamma 0 and gamma 1 if the curve is a geodesic. So you play with that you apply the Young inequality to the right-hand side, and it's not hard to check that you have this inequality. And this inequality becomes an equality if the function f is actually the distance squared from, from our given, final point x, just by, direct computation. So basically, you just Taylor expand this inequality, and you're done. So you write this. So you write the inequality for f equal the given nice function plus epsilon g. You subtract the epsilon, you expand basically, and what you get is this inequality holds for every g and every epsilon, and epsilon can be positive or negative. So this inequality at the end will not matter, and we get the desired differentiation. So that's. Thank you. Yes, I mean, yes, of course I have in principle, but in fact, I can prove, actually Rayala proved that I can select a geodesic where mu t, along which the entropy is convex, and mu t has bounded densities, at least as far as, not at t equal 1, but in every subinterval, 0, 1 minus epsilon, it has uniformly bounded density. And that is the only regime. Yeah, you're right, of course. I mean, I cut some corner, but the point is that I'm only caring about these mu t's for t close to 0. So in the end, that's okay. But you're right. In principle, that I should check. Please, Robert. Yes, that's also true. That's also true. I didn't want to get into that. Yes, but that's also true. Yes. All right. Yeah, I only need convexity. All right. Yeah, in the last 4 minutes, I guess, let me just tell a couple of things about second-order calculus, just a couple. And the first one is this, is that it concerns lower Ricci bound in the smooth setting. So a lower Ricci curvature bound in the smooth setting can be characterized via the Buchner inequality. Okay, so the Buchner inequality is this inequality over there. So this is true for any smooth function if and only if the Ricci curvature is greater than k. Okay, this is a crucial inequality. I must say I'm surprised. So there is, I know no analog of this inequality in the Lorentzian case, and that is in some sense is a reason of concern. Okay, because second order calculus on RCD spaces is all built around this kind of inequality. And now, but still concerning, so in some sense I think it's a challenge. And I mean, if I have to take inspiration from the elliptic case, we should understand what this is in the Lorentzian case. And now, an interesting fact is that if this inequality holds, in fact, a stronger inequality holds. So this is a classical case of a self-improving of an inequality. Right? So you know something, and then immediately you know something better. In some sense, you can put an Hessian squared, which is positive, on the right-hand side. And why can one can do so? Well, because there is the Bochner-Weizenbach formula, which is tell me, I mean, this is a computation. The Laplacian of the squared differential equals this. So if you are in the flat case, there is no Ricci curvature. You commute all the derivatives that you want. If you are on a Riemannian setting, you have these Ricci curvature terms, and then it's easy to see that this one above implies the one. Yeah, of course. But the problem is that the Hessian has no sign. So I mean, as we discussed, and yeah, so we cannot have this Buchner inequality. Yeah, of course, this is just algebra if you want to. Now the point. Now I really make a long story short, but the point is that this Buchner inequality, in some sense, in some weak sense, holds true even on RCD spaces. Okay. And if it holds true, and once you have this inequality, you see that you have, typically, you can have bounds on scored Hilbert-Smith norm of the Hessian. So what you can do, and this is something that on RCD spaces I've been done, like almost 10 years ago, and more recently Brown, Matthias, generalized this to, a class of spaces where the Ricci curvature is not uniformly bounded from below by a number, but maybe by a distribution. So in particular, it covers at least some, if not all, of these tamed spaces that Chiara Rigoni is going to speak about after me in a few minutes. But basically what you can do, you can define a concept of W2 functions and that of Hessian. So once you have this technology, this algebraic machinery of L2 norm del infinity module, you can start taking tensor products and operations of this form. So a home for an Hessian is easily built in some sense. And you can prove that you have many W2 functions. And similarly, you have a concept of Sobolev vector fields. So not only vector fields in the sense of elements of an abstract module, but also Sobolev regularity. And similarly, the Sobolev regularity for forms, so you have the whole, the RAM cohomology and Dodge theory is there. And you can also define, you can now use the Bochner-Weizenbach formula to define what is a Ricci curvature tensor. And not surprisingly, this Ricci curvature tensor will be measure valued and bounded from below by K in a space that has Ricci curvature bounded from below by K. So in some sense, this reflects the K that it is in the definition of RCD K infinity. Now I conclude with a reason of concern, and which is about what we will ever be able to obtain, supposing and assuming that we will be able to run this whole program in the Lorentz analog. And there's something that I think is worth to point out, to pose a bit, and to consider. And the point is that in general, this Ricci tensor that I just defined in the last slide, which is a measure, it's a measure that does not see spaces or sets, of codimension 2. Okay, by nature, this has something to do. The technical point has to do with the so-called capacity of a set. So it does not charge set of null capacity, and set of codimension 2 have null capacity. Now, unless we know something about, unless we have very good information about the local structure of the space. If we know that, then we can do something, as John Lott has proved. But in general, we do not. So now, why do I care? Well, because if we want to run a non-smooth theory of general relativity, and we want to say write down the Einstein equation and get some sort of information about the stress energy tensor in some singular way. In particular, maybe I have a cosmic string. A cosmic string is something of codimension 2. I would like to see some sort of Hausdorff measure over there. This by nature, it cannot be seen by an object, by a distributional object of the form that I just described, unless we know something very strong about the local geometry of the space. So in some sense, this is, I think, is something that one should keep in mind. It's not that you write down the Ricci tensor and basically everything is there. So there are serious regularity issues that both in the elliptic and I think also in the hyperbolic case are crucial are crucial. Okay, and that's it. Thank you for that.